Ladies and gentlemen, welcome to the afternoon session. In the early days of planning this conference sometime last year, one of our sponsors, the European Physical Journal, suggested we had a named lecture, a keynote lecture, which they would be happy to support. And we thought about that for quite a few minutes, and we discussed the usual suspects. And then we thought, well, look, Strong and ElectroWeak Matter, there's going to be a lot of stuff about spontaneous symmetry breaking. There's going to be interesting applications. Today we've heard about applications in dense baryonic matter. Tomorrow I think we're going to hear about applications in the early universe. So it's clearly an idea which has got a lot of legs. And why don't we invite the originator to come and tell us a little bit more? And that was pretty much how we sold this idea to Peter. We may also have mentioned the banquet this evening. I don't know if that had any influence on him. And so we asked him, and everything was running really smoothly. And then around about the turn of the year, one of our colleagues said, did you know there's this new accelerator in CERN? They've actually seen quite a few excess to photon events at about 125 GeV. And we thought, yeah? And then they took us aside and explained a bit about what that actually might mean. And soon it became clear that we might have quite an event on our hands. And by June, that was only still more clear. The excitement was mounting. In fact, we tried to get hold of Peter to arrange make the arrangements of today. We left messages on each other's answer phones. And he actually told us there's no chance of a 5 sigma, so don't make any big deal about it. Don't invite the press. So we didn't. That was about 2.5 weeks ago. But we all know what happened next. And I think we were all thrilled last week to see those amazing and moving scenes from CERN. And so I'd like to introduce the European Physical Journal speaker. He is a winner in 1997 of the Dirac Medal from the Institute of Physics. In the same year, he won a medal for high energy and particle physics from the European Physical Society. In 2004, he won the Wolf Prize for Physics. And in 2008, he was made an Honorary Fellow of Swansea University. I'm sure we'll all agree that Peter won the biggest prize of all 8 days ago. It gives me much pride and pleasure to introduce the most recognizable physicist on the planet, Peter Higgs.
Well, thank you, Simon. I think I should start with an apology to at least one person who first heard a talk from me with this title in Swansea as long ago as 2001. The transparencies are the same. The talk has evolved a little. So I will begin by introducing my life as a boson. The title is actually cribbed from a Swedish film of many years ago by Lasse Hallström, who's recently responsible for salmon fishing in the Yemen. The title of his film was My Life as a Dog, and when I gave a talk with this title in Stockholm some years ago, it was the way I'd cribbed the title was recognized by some of the people in the audience. So what I plan to do in this version of the talk is to talk perhaps for about half an hour on the way I was involved early on in the 1960s in spontaneous symmetry breaking in particle physics, and in the last quarter of an hour perhaps I'll fast forward the story up till the present and comment on the events of the last few weeks. So, the way in which spontaneous breaking of symmetries, that is, symmetries described by Lie groups, continuous rather than discrete symmetries, how the idea of spontaneous symmetry breaking was imported into particle physics. It goes back to the BCS theory of superconductivity in 1957. It comes into particle physics through the work of Yoichiro Nambu and Jeffrey Goldstone in around 61, and the later part of it is the work of Braut and Ongle and myself and Guralnik, Hagen and Kibble in 1964, and as I'll just describe, what we did then was really patch up an omission from what Nambu had done earlier. And then of course, as you know, this was applied to ElectroWeak theory, of the theory formulated by Shelley Glashow, published in 1961, and it was, as it were, bolted on to the spontaneous symmetry breaking models by Weinberg and Salam in 67, and then it became, shall we say, fashionable after this kind of theory was shown to be renormalizable in perturbation theory by Feltman and 't in especially 't in 1971. So I'll talk, as I say, first of all, about that period and then bring it up to date. So the story begins when I was appointed to a lectureship at Edinburgh in 1960. I was asked to be a steward at the very first Scottish University summer school in physics, where the students, the participants, included Nicola Cabibbo, Shelley Glashow, Derek Robinson and Tini Veltman, and of those four there are so far two Nobel Prize winners and sadly one near miss. They were the gang of four who stayed up half the night discussing theoretical physics, especially I suppose electroweak theory, and I wasn't part of that because I had work to do and had to get up in the morning. But some of the people in that list will reappear in my story later. So briefly, I'll just indicate the early history of spontaneous symmetry breaking of this kind. It begins with Heisenberg's model of ferromagnetism and the existence of a degenerate ground state for a system at infinite volume in condensed matter theories. The theory of superfluidity is the next stage, which involves a Bose condensation, and that was first discussed, I think, by Bogolyubov in 1947, and the symmetry there is of more relevance to the later elementary particle theories because it's not geometric, it's the symmetry under a transformation of phase of a complex wave function. Psi goes to e to the I alpha psi, and it's a global U1 symmetry. We get closer to elementary particle theory with superconductivity, with a charged Bose condensate. First of all, with, well, I've said Landau and Ginzburg, but I get into trouble with various people from Russia when I describe it. So it's actually Ginzburg and Landau. Ginzburg was the first author of the two, 1950, who applied the same ideas to same ideas as in superfluidity to charged spinless particles. And the trouble was that they weren't taken too seriously as proposers of a theory of superconductivity, because nobody could say where you got charged spinless particles in a metal or alloy. And the breakthrough came with the insight of Cooper and then the BCS theory, where it was realized that the spinless particles undergoing Bose condensation could be composite, made out of electron pairs. Particle theories, well, the Heisenberg theory of ferromagnetism probably influenced Heisenberg's ideas of 1958, nonlinear spinor theories, but the Heisenberg theory of 1958, which was at one time Heisenberg and Pauli, was not really believable because of how it was, how people calculated with it, and so that didn't really have much impact. The theories which did have an impact, the theory was the BCS theory, and it came about as a result of Schrieffer moving from the University of Illinois to Chicago University for a year, where Nambu learnt about BCS theory, and he then was one of the people who changed the formulation of BCS theory from the usual sort of many-body quantum mechanics into a quantum field theory language, and this made the importance of spontaneous breaking of a gauge symmetry rather more clear. Nambu then realized that these ideas might have application in particle physics. And the models which he proposed in 1960, in particular this one, were models in which spontaneous symmetry breaking in relativistic quantum field theory modeled very much on BCS theory, something involving pairing of fermions and then a condensate, these models were such that spontaneous breaking of a chiral symmetry turned what were apparently massless spin half particles into massive spin half particles. And this is really the beginning of the generation of mass by spontaneous symmetry breaking in elementary particle theory. The analogy here is that in the superconductor, you have a change from the partially filled energy band that you have in a conductor, where the electrons can be excited to neighboring states in the empty part of the band with as little energy as you please. But the BCS mechanism, the condensate, produces a gap so the electrons can no longer do that, and it's the condensate which carries the current. That's rather similar to the difference between a massless Dirac particle, where there is no gap between the filled C and the empty positive energy states, and a massive Dirac particle where there is a gap of 2mc squared. So essentially the models which Nambu wrote down were producing a mass gap in the same way as BCS, and doing it for spin half Dirac particles. Goldstone simplified the ideas involved considerably by writing about field theory models involving elementary scalar fields, where you trigger spontaneous symmetry breaking with the now famous wine bottle potential. And the Goldstone models are like the Ginzburg-Landau model for superconductivity. They're simpler to understand, but maybe it doesn't necessarily follow that that way is correct, of course. And here's a comment which Robert Brout, who unfortunately died not very long ago, quotes from Weisskopf at a Cornell seminar. Particle physicists are so desperate these days that they have to borrow from the new things coming up in many body physics like BCS. Perhaps something will come of it. That's, I think, the seminar which triggered Brout's interest in this kind of physics, because Robert Brout, until 1964, was known mainly for his work in condensed matter physics and phase transitions, and he worked at University of Brussels, where the department was very much oriented toward condensed matter and statistical physics. Now, the trouble with Nambu's way of doing things, which was essentially a BCS-type model, but not including electromagnetic effects, was that one of the results of spontaneous symmetry breaking was to produce some massless, spinless particles. The Nambu-Yornalicino model was a broken chiral SU2 cross SU2 with input as massless proton-neutron, because this was before quarks were invented, and they produced a bound state which looked like a triplet of pions, but it was massless. And Goldstone made that phenomenon intuitively obvious in models with elementary scalars, because the massless states are the excitations around the trough of the wine bottle potential. The theorem was then formally proved by Goldstone, Salam, and Weinberg in 1962. I should perhaps say the paper was written by Salam and Weinberg, and Goldstone agreed to add his name at the last minute. That's because Goldstone, I think, is reluctant to publish papers. He's published very few. So the theorem said, in a manifestly Lorentz invariant quantum field theory, if there's a continuous symmetry with the invariant Lagrangian, the Lagrangian invariant, then either the vacuum state is also invariant, so there's no spontaneous symmetry breaking, or if the vacuum state is not Lorentz invariant, there must exist particles of zero mass and zero spin. And that was the stage at which I began to get more involved. I'd been certainly very interested in Nambu's program, and I tried to formulate models without Goldstone particles, and it clearly didn't work. So in the years 63, 64, there was a debate in the literature about whether it was possible to evade the Goldstone theorem. And let me just get my piece of paper to do some screening. The first man to suggest that it was possible was, in fact, Philip Anderson, a condensed matter theorist. And what he did was to point out that in a superconductor, the Goldstone mode becomes a massive plasmon mode due to its electromagnetic interaction. And this mode is just the longitudinal partner of transversely polarized electromagnetic modes, which have become massive. In other words, there's a minimum frequency with which they propagate. This is what gives rise to the Meissner effect, the exclusion of magnetic flux from a superconductor. And then Anderson continued by saying the Goldstone zero mass difficulty, and he's referring to relativistic theories, is not a serious one because we can probably cancel it off against an equal Yang-Mills zero mass problem. However, the trouble with Anderson's paper was that he really didn't address the situation as it was in 1963, because he didn't confront the theorem, and people were beginning to believe that in a relativistic theory this couldn't work. And the other thing is what he didn't do. He didn't actually discuss any specific relativistic model. He just clearly felt it was obvious that it would work relativistically as well as non-relativistically. Well, of course, it turned out that he was right. So the next stage in 1964 was, no, I'm going to skip this one, it's too technical. This was the further discussion on how to evade Goldstone's theorem, and there was a sequence of short papers in physical review letters arguing back and forth about this, and the crucial stage was, for me, first of all, Abraham Klein and Ben Lee in March 64 argued that, there's a technical bit there, but it's a question of a spectral function when you look at the vacuum expectation value of the commutator of a generator of the group with a scalar field variable, but I'll skip the technicalities. The point that Klein and Lee made is that in something like a superconductor, this spectral function has a more general form than in the discussion by Goldstone, Salam and Weinberg, and the more general form allows you to evade the Goldstone theorem, but the more general form involves something which specifically picks out a frame of reference, which is for something like a superconductor, the frame of reference of the background in which the superfluid moves. There is a preferred frame of reference relative to the superconductor. And they thought maybe this could be done relativistically too. In June 64, Walter Gilbert, who was in transition from being an elementary particle quantum field theorist to being a molecular biologist, wrote a short note saying, no, this is impossible. Anything involving a preferred frame of reference violates Lorentz invariance, relativity, so it can't be done. And then that was what I reacted to, first of all, in annoyance and frustration, because he seemed to have closed the door to the whole program. And in July '64, after reading his paper, which took about a month to cross the Atlantic by snail mail, I realized that there was a way out. And that the way out was if you have a gauge field, in other words, field of an electromagnetic type coupled to the current associated with the symmetry. So I'll now tell you a little about how that happened and how it was associated with the remarks I made about the existence of what's now known as a Higgs boson. So, 1964, over a weekend after reading Gilbert's paper, it struck me that his arguments didn't apply when there was a field of the Maxwell type present, because in the quantum field theory of that kind of field, which has a singular Lagrangian, you have to do some gauge fixing. And gauge fixing, which means constraining the freedom which the potentials have, can certainly be done in a way which is not manifestly covariant, Coulomb gauge, though people prefer to do it in a Lorentz covariant way, but then at that time, Lorentz gauge quantum electrodynamics, though practically useful, was a rather odd business. It was really finally clarified, I think, by Tom Kibble later. So the week after reading Gilbert's paper, which I read on the 16th of July, the Friday of the following week, a short paper which I wrote was sent off to physics letters saying there's a way out, it's gauge theories, and it was accepted. Then, of course, having realized this might be done, I had to see what it actually did for the physics. So what I did was think of the simplest possible non-trivial model, which is now called the Higgs model, and what it amounts to is bolting together the simplest model discussed by Goldstone with Maxwell theory. That's all there is to it. And when I did that, of course, I saw that Anderson was right all along. You do have the relativistic analog of the plasmon phenomenon. The Goldstone modes, which used to correspond to spin zero particles when they were massless in Nambu's models, now become the extra states which you need for massive spin 1, compared with a photon, which has only 2 polarizations. That spin 1 massive requires 3, and that's exactly what happens. So I sent off that paper to physics letters. I was being a good European at the time, and we were being encouraged to send things to physics letters, not physical review letters. So I sent it off, and it was rejected. So I was a bit upset about that, and I thought, well, really, why did they accept the previous letter, which simply said it can be done, and then they reject the second letter, which says this is how it's done? So I revised it in August by adding some extra material which I thought might suggest that there were some physical consequences of doing things this way. And one of the remarks I made was, it is worth noting that an essential feature of this type of theory is the prediction of incomplete multiplets of scalar and vector bosons, and the scalar bosons meant essentially the spin zero massive particle or particles in the theory, of which there must be at least one. I mean, if you've got that happening for a very simple kind of symmetry, a U1 symmetry, it doesn't go away when you enlarge the symmetry. And this was, to me, not surprising, because, well, the massive partner of the Goldstone bosons had been there all along in the theory without gauge fields. It just didn't get affected by putting in the gauge interaction. And recently, when Frank Close asked, well, I'm not sure whether it was Brout when he was still alive, or maybe Angler, why they didn't mention it in their paper, which, as I'll be describing, was written just before mine. Why didn't they say this too? They said, well, it's obvious, and it is obvious. So the revised paper went across the Atlantic. I wasn't going to risk a second refusal from Physics Letters, and it was accepted. And many years later, in 1984, I discovered that Nambo had been the referee of that paper, so he understood what I was doing. But he drew my attention to the paper by Angler and Brout, which had been received by Physical Review Letters earlier in June, before I even had my insights, and it was published on the day that my second paper arrived. So that was the birth of the boson as far as I was concerned. So now I think I have to briefly fill in what happened next, and then conclude by saying something about the last few weeks. The following year, I got round to writing a longer paper, essentially showing how you would do some calculations at the tree level with the simple model I'd written down. By that time, I was at the University of North Carolina at Chapel Hill, and I sent off, preprints were sent off to the circulation list which they had at Chapel Hill. And one of the people who received one at the end of '65 was Freeman Dyson, and I got a very nice letter from him which said roughly, your paper has helped me to understand some things which I've not understood before. And from Dyson, that was really a big compliment. And so he invited me to give a talk about it at the Institute at Princeton. And that I did in March '66. And at the same time as I accepted the invitation from Dyson, I wrote to my friend Stanley Deser at Brandeis, telling him that I was going to give a seminar. We'd previously met at a conference in London, and he'd said, when you're giving seminars up the East Coast, let me know, and I'll arrange something in the Boston area. So I gave a seminar at Princeton at the Institute before an audience largely composed of axiomatic quantum field theorists who thought the theorem, the Goldstone theorem, had been proved really rigorously using C-star algebras. And before I gave the talk, Klaus Hepp, whom I'd met some years before, told me I must have made a mistake. because Castlear Robinson, or that's the Derek Robinson of the Gang of Four, and a man whose name I don't know the pronunciation of, is Svietza. Aubrey, you probably know. Anyway, he told me I must have made a mistake. But I heard afterwards that I'd convinced Arthur Whiteman that there was something in this, and therefore I got by it at the Institute. And the next day at Harvard was a much more lively occasion where my seminar turned into a kind of dialogue between me and the audience. And I learned afterwards that when I met Sidney Coleman a second time in 1979, he said, "Oh yes, I remember you." Back in 1966, we, meaning he and his friends, were looking forward to tearing apart that idiot who thought he could get round the Goldstone theorem. But anyway, I think I won on points at that seminar too, and the slightly sad thing about the occasion was that Shelley Glashow was there and came up to me after the seminar and said, "That's a nice model, Peter." But it didn't occur to him that it might do anything for what he had formulated back in 1961. And I hadn't really heard enough about his ElectroWeak theory because, as I say, I was busy when the Gang of Four had their discussions. And anyway, as I discovered years later from Nicola Cobibo, they'd been smuggling wine, which I was supposed to look after as the steward of the school. They'd been smuggling it into a little cache in the grandfather clock in the basement of New Battle Abbey College, where they held their discussions. So I didn't know as much about Glashow's work as I should have done. Okay, so I must get to the end of this part of the story. I'm sure you know all about the subsequent stages involving Weinberg and Salam and Feltman and 't Hooft, and the consequence of 't Hooft's proof that massive Yang-Mills theory can be renormalized provided that the mass comes from spontaneous symmetry breaking. That was presented at the Amsterdam EPS conference in 1971. And then a year later came the big high energy physics conference at Fermilab, 72. And at that stage, the rapporteur on the subject of ElectroWeak theories, Ben Lee, plastered my name all over everything to do with spontaneous symmetry breaking in particle physics. And the other people involved were simply mentioned in a footnote, and I think they didn't like it. I think the reason this happened was that I met Ben Lee, that's the Ben Lee who was part of the debate on the Goldstone theorem. I met him at a conference in Rochester, New York State, in 1967, and the conversation in which he asked me more about my work was conducted with me holding a plate in one hand and a glass of wine in the other at a party at the end of the conference. And I didn't perhaps give all the detailed references to other people's work that I could have done in other circumstances, but I think he should have done more homework on it. 1975, after the discovery of weak neutral currents, is a crucial year. The paper was published 76, and this is the paper by John Ellis, Mary K. Gaillard, and Dimitri Nanopoulos, a phenomenological profile of the Higgs boson, in which they say we should perhaps finish with an apology and a caution. We apologize to experimentalists for having no idea what is the mass of the Higgs boson, unlike the case with charm, and for not being sure of its couplings to other particles, except that they are probably all very small. For these reasons, we do not want to encourage big experimental searches for the Higgs bosons. But we do feel that people performing experiments vulnerable to the Higgs boson should know how it may turn up. Contrast 1989, just around the time when LEP began to operate, and the four people who wrote the Higgs Hunter's Guide, which was intended for people at the ill-fated superconducting super collider in Texas, said the success of the standard model has been astonishing. That was essentially what had been already discovered and measured at LEP. Sorry, not at LEP. This was the things which had been looked at even before LEP started up. The central problem today in particle physics is to understand the Higgs sector. So that was a sort of shift of emphasis over these years. So let me come up to recent events. As you have heard, after LEP didn't quite get there, in spite of some apparent discoveries when the machine was about to be switched off, which turned out not to be believable because there were other sources of background. The story since has been the narrowing of the window for the Higgs search by precision measurements, some of them at LEP, but later on particularly at the upgraded Tevatron, which was the upgrade was intended to look at the region where LEP had finished and where the LHC would find it difficult to search, and the hope was that the Tevatron could get there first. But even if that didn't quite happen, what they really achieved was to do precision measurements on things like the top quark mass and the W mass in such a way as to place much stronger constraints on where the missing particle should be. And so, well, the last year has been interesting. There were the hints in July a year ago, which triggered some people in Edinburgh who should know better to congratulate me. I think the people who did that would have been better professionally if they'd understood a bit more about statistics, frankly. There was the update in December at which it began to look as if it was really going to arrive sometime within this year. And before the December announcement, I got a message from Rolf Hoyer saying you should pay attention to what's going to be announced, but don't be too optimistic. It won't be of the standard which we need for a discovery claim, but that might follow, or at least, I mean, he didn't put it quite this way. He said the matter will be resolved one way or another within the coming year, 2012. And I was expecting it to be fairly late in 2012. But then, in the last few weeks, I've been giving talks and doing various things at various places around the country which have people working on Atlas and CMS. and I had seen a blog which suggested that although the amount of raw data was plenty to settle the matter, the analysis couldn't happen to the extent of a conclusive announcement in time for the Melbourne conference. And the people I talked to on Atlas and CMS in early June agreed with this. So much so that when I went to the summer school at Erice on Monday, June the 25th, I didn't take any Swiss francs with me, and my travel insurance expired on Monday, July the 2nd, when I was due to fly back to Edinburgh. During the week at Erice, there began to be hints that the pace was quickening. There were people at the summer school who obviously knew a lot which they couldn't really communicate to people who weren't in the know. People like Peter Jenny, the former spokesman for Atlas. Tejinder Verdi, who was to have given a talk on CMS towards the end of the week, cancelled. Some of us thought maybe he was worried about giving away too much before the CERN seminar, but he says he was just very busy, which I can believe. Towards the end of the week, we began to get signals from CERN that it might not do any harm if I went to Geneva on Wednesday, the 4th of July. They weren't inviting me, but they would be happy to see me and would reserve a place in the lecture hall. Then it was discovered that Jerry Guralnick and Carl Hagen had invited themselves. The next news, I think, was that Francois Anglaire had decided to come and was getting some encouragement. And the final stage came on Saturday, June the 30th, over lunch, when a message came through to my colleague Alan Walker from John Ellis, who said, "Tell Peter that if he doesn't come to CERN on Wednesday, he will very probably regret it." At that point I said, "Okay, I'm going." And before the seminar, on the Tuesday evening, Alan Walker and I were invited to dinner with John Ellis outside Geneva, and another of the guests was Chris Llewellyn-Smith, who was staying with him. And before dinner, John opened a bottle of champagne. So that suggested what the next day was going to be like. But the actual seminar itself was an amazing experience. It was a very emotional occasion for a lot of people. And at the end, when the 5 Sigma discovery was announced, people really went wild. There was a standing ovation for the experimentalists. There was stamping and clapping, and it was a bit rather more like the end of a football match where the home team has won than a scientific seminar. So that was it. That was it. I mean, the announcement from Rolf Hoyer was still, of course, cautious because there was still a lot of measurements to make. But he said, "I think we've got a Higgs boson, not the Higgs boson. We still have to find out more about this particle." And so that's I think the conclusion of one phase of my life as a boson. Thank you.
time for some questions. I wonder if there are any. Mark.
So now that we've got the discovery, lots of physicists are being asked by their friends, what difference does the Higgs boson make to the world around me? So could you say something about, for example, which properties of an atom are determined by the Higgs boson and which are not so dependent on it?
Which properties of an atom are determined by the Higgs boson?
Of an atom? I mean, I think when you're looking at atoms, molecules, the whole of chemistry and the whole of biology, a great deal of the particle physics that we know and love is rather irrelevant, because to a large extent, all you need to know about is electromagnetic interactions and quantum mechanics, and well, even things like the existence of the weak interactions and radioactive decays are more of a nuisance in, shall we say, biology than any help in understanding. Is that a fair answer to your question?
Well, I guess I was thinking maybe the fact that the electron gets its mass from the Higgs.
Well, okay. So the I mean, first of all, of course, I don't think I need to remind this audience that the way that some people talk about the Brout-Englert-Higgs-Guralnik-Hagen-Kibble et al. Mechanism gives mass to all of matter. That's not the case. It provides a sort of initial seeding of the mass. It gives it to the leptons maybe, and it gives it to quarks. But when it comes to anything more complicated than the quarks, like nucleons, there are far more important things involved, like the way that quantum chromodynamics works. Okay, well. Maybe the explanation of the electron masses is right. That I think I believe. But as far as atomic physics and chemistry and all the rest are concerned, who cares?
We're in a lecture theatre which was formerly part of the chemistry department. Do we have any other? Yeah, Tom.
So from your remarks, I understand that you first heard the word Higgs boson from Ben Lee. Is that how it entered physics?
Oh, the term. I think the term Higgs boson began to be used by people around the time of the paper by John Ellis et al. In the mid-70s. At the time that Ben Lee gave the talk in 1972, what he actually said was Higgs meson, but then people got fussy about terminology, and meson is now reserved for hadrons of the right sort of spin. So it was Higgs meson then in 1972, but then it was that my name was applied to everything, and I more or less disowned it. That in 1984 at a conference on the history of weak interactions in Racine, Wisconsin, and said the only thing I think might be justified having my name attached is the Higgs boson, because I think I was the only one who explicitly pointed out that it should be there. As I told you, Brout and Englert thought it was obvious anyway.
Can I ask actually a technical question? What is your personal opinion on the use of the term God particle.
He wants to know your opinion of the use of the term God particle.
Oh, I mean, for me, it's simply an embarrassment because I mean, I have never used such a term, and I never would. And it was, after all, a kind of joke in origin, where Leon Lederman's publisher didn't like the title "That Goddamn Particle," which he wanted to give to his book because the particle was so difficult to find. So I wish he hadn't done that, because it leads a lot of people who should know better into rather spurious theological speculations. In other words, I don't like it.
Any further questions? Maybe from somebody who's not at the conference. Thomas.
So I noticed that in the paper you actually consider Higgs goes to 2 photons, so that's somehow remarkably prescient. No.
He said,
For 40 years nobody believed that would be the channel.
yes, he's pointing out that you noticed the Higgs goes to 2 photons channel in your original paper.
Oh, I don't think I did. I thought I think the only decay I discussed in my 1966 paper as an example of how you would do calculations at tree level was a conjectured Higgs boson into 2 spin 1 particles, two massive, I think it was that, into 2 massive spin 1 particles which were in the original model, but that's not a photon. So it's nothing much to do with the real 2 photon process, which after all is a 1 loop process. These are all tree level things within the calculations in the specific model.
So, if my mother asks me when I come back from this conference, what is the Higgs boson? She doesn't know anything about physics. What would you say to her?
How would you explain the Higgs boson to his mother?
Well, I find it difficult enough explaining the so-called Higgs mechanism to people who are not physicists, and I don't like some of the explanations which are given by some physicists who I think should know better. And all I can say is that granted a whole lot which probably wouldn't be comprehensible anyway, you simply have to have a Higgs boson in the theory because you've generated masses using this background field, the so-called Higgs field, whatever that may be, and in principle you might think, well, you don't need to have a particle as well. It's the background field which generates the mass for the others according to how they interact with the background. In principle, you could look at the theory and freeze out the excitation of that field, which is the Higgs boson, by some device like making its mass go to infinity. But if you do, the theory becomes nonsense. And this is already known from work by, for example, Chris Llewellyn-Smith, and also I think on the other side of the Atlantic, Cornwall, Tiktopoulos and others, in the early 70s, when they took the opposite point of view from the way the theory was set up to say, how would you generate a theory in which the particles in scattering had the right, the scattering of the particles had the right high energy behavior, which means decreasing, not increasing, because any increasing amplitude in scattering then gives rise in perturbation theory to unacceptable behavior of the quantum corrections. So you have to make the scattering amplitudes of the particles you've got decrease with energy, and well, Chris, I mean, his work is the one I know best, showed first of all to do it for a theory involving spin 1 massive particles. You need to make it a spontaneously broken gauge theory. But there's one thing left that you've failed to do by just having the background field to produce spontaneous symmetry breaking. There's the scattering amplitude for the longitudinal components of the spin 1 bosons, one on another, say W1W, and that still fails to decrease in a way which violates unitarity. So you've got to put in a Higgs boson as an excitation to cancel that off. So that's a way you convince phenomenologists and experimentalists that they've got to take it seriously.
So you see, Mum, it's all to do with unitarity. I'm really sorry. I'm afraid that's all we have time for. The session now comes to a close. Can I, on behalf of us all, thank you, Peter, for sharing those insights with us. I feel we've all lived a little bit through a little moment of history along with you, and it's been absolutely thrilling to hear those reminiscences. Thank you again.